The precise definition of a limit. Let f be a function defined on some open interval that contains the number a, but it may not be defined at a itself. Then we say that the limit of f of x as x approaches a is L, and we write the following notation. If for every number epsilon that is positive, there is a corresponding number delta that is also positive, such that whenever the distance between x and a is less than delta, then the distance between f of x and L is less than epsilon. When you first hear this definition, it's very common to be confused. So here we have a couple of diagrams to help us think about what the definition is really saying. Intuitively, we understand what it means to be a limit. We know that as x is getting closer to a, the values of f of x have to be getting closer to L. And you can see that is the case here in this diagram. But to make that definition precise, what we do is we choose a small positive number epsilon. And epsilon is going to be the distance between L and the upper limit here and L and the lower limit here. And we want f of x minus L in absolute value to be less than this value of epsilon. So if you have your function value, wherever that is, and you subtract L, that distance needs to be smaller than epsilon. What that means is you want the function values to be between these two horizontal lines. And we can make this value of epsilon as small as possible. So over here in the next diagram, you can see that they've taken the value of epsilon and made it even smaller than what it is here. And your function values will always be between those epsilon bars as long as x is sufficiently close to a. What does it mean for x to be sufficiently close to a? Well, it means the distance between x and a is small. How small? Well, it has to be less than some delta. So if we choose a value of x within delta units of a, the f of x will always be within epsilon units of L. That's the concept. Let's take a look at an example. Here we want to prove that the limit as x approaches 3 of the function 4x minus 5 is equal to 7. Now we know this is true based upon the limit laws that we've learned in previous lessons. But now we want to prove this using the precise definition of a limit. So if we have the limit as x approaches a of f of x is equal to L, this is only true if the absolute value of x minus a is less than delta, means that the absolute value of x minus L is less than epsilon for any arbitrary epsilon. So if we have an epsilon, a really small positive number that is given to us, then we need to be able to find the corresponding delta such that if x minus a in absolute value is less than delta, then f of x minus L in absolute value will be less than epsilon. So what you do is you work backwards. So we're going to start with the conclusion. We need f of x minus L to be less than epsilon. Now in our particular problem, f of x is 4x minus 5, minus L is 7, And in absolute value, we need that to be less than epsilon. Now, if you simplify here, you get the absolute value of 4x minus 12 is less than epsilon. And then we can factor a 4 from this. And then we can use a property of absolute values that says if you have the absolute value of one thing times another, you can take the absolute value of the first thing and multiply it by the absolute value of the second thing. The absolute value of 4 is 4. And now if I divide by 4, I get the absolute value of x minus 3 must be less than epsilon divided by 4. Now I want you to notice in the end here that this is x minus a, because in this problem a is 3. So what we have here is the absolute value of x minus a must be less than epsilon over 4. And this epsilon over 4 is our delta. Now, this is actually the work for the proof. How do we prove that this limit actually exists? Well, the way you prove it is you have to show that whenever this is true, this will be true. So now let's walk through the actual proof. I'm going to say, if we choose delta to equal epsilon divided by 4, then if the absolute value of x minus 3 is less than delta, this means the absolute value of x minus 3 is less than epsilon over 4. And if I multiply both sides by 4, I get 4 times the absolute value of x minus 3 is less than epsilon. So all I'm doing here is multiplying the left and right side by 4. But we know that 4 is the same as the absolute value of 4. And so we have the absolute value of 4 times the absolute value of x minus 3 is less than epsilon. And now I can combine this into a single absolute value. And then I can multiply this out. And now we can separate this to be the absolute value of 4x minus 5 minus 7. Now, of course, how do I know that I need to do this? Well, again, I know what my function is, right? I know I have 4x minus 5 in the beginning. So when I get down to 4x minus 12, I'm going to write that as 4x minus 5 and then minus 7. And now you see what we have there is the absolute value of f of x minus L is less than epsilon. So if we're given any positive small number epsilon, all we have to do is choose delta to equal epsilon divided by 4, and then anytime x is within delta units of 3, f of x will be within epsilon units of L. And this is how you prove a limit using the precise definition. This next example is a little bit trickier. Here we want to prove the limit as x approaches 3 of x squared is equal to 9. Now, of course, we already know this is true because x squared is a polynomial, and we can plug 3 in here to get 9. But that's a limit law that we take for granted. How do we prove this definition precisely? So again, the precise definition of a limit says that anytime the absolute value of x minus a is less than delta, you will get the absolute value of f of x minus L to be less than epsilon. So just like in the previous example, we are going to start by working backwards. So we're going to start with the absolute value of f of x minus L needs to be less than epsilon. In our particular problem, f of x is x squared, L is 9, and we need that absolute value to be less than epsilon. Now I'm going to factor x squared minus 9 turns into the absolute value of x plus 3 and x minus 3 less than epsilon. And then we can use a property of absolute values to separate this into the product of two separate absolute values. Now keep in mind you're trying to get to this step, and in our example a is 3, so we need the absolute value of x minus 3. So this is what we're looking for here. Now in the previous example this was a number, but now this is a variable expression. So we have to think about how big is this number here. So let's go to a number line. Now we know that we're taking the limit as x approaches 3, right? And we're approaching 3 from either the left or the right. And since we're approaching 3, it is safe to assume that the number x will be within 1 unit of 3 at some point. So on our number line, that means that at some point we can expect our x to be somewhere in between 2 and 4, right? Does that make sense? If we're approaching 3, wouldn't it make sense at some point you would have to be bigger than 2 or less than 4 if you're approaching 3? So what this means is that it is safe to assume at some point that x will have to be a number in between 2 and 4. Now what I'm trying to do is figure out how big would x plus 3 be. So to understand this, I am just going to add 3 to all 3 parts of this continued inequality. And that's going to give us 5 is less than x plus 3 is less than 7. And let's just take this side of the inequality. If x plus 3 is less than 7, then we know the absolute value of x plus 3 would have to be less than 7, right? Think about that for a minute. If x plus 3 is a number, and that number is somewhere between 5 and 7, then we know for sure the absolute value of x plus 3 would have to be less than 7. Okay, so what does this mean? So now continuing down here, we know the absolute value of x plus 3 times the absolute value of x minus 3 must be less than 7 times the absolute value of x minus 3. All I'm doing here is I'm using the fact that we know that this number is less than 7, as we stated over here. And we want this, ultimately, to be less than epsilon, as we have stated up here. So if that is the case, then the absolute value of x minus 3 would have to be less than epsilon divided by 7. And this is our delta, right? Because this is the absolute value of x minus a, needs to be less than delta. So now the proof of this limit would just be the same steps in reverse, just like we did in the previous example. So basically, if we are given an epsilon greater than 0, we need to choose delta to equal epsilon over 7. Again, this is assuming that x is some number in between 2 and 4. And then from there, we can work all the steps backwards. So I have the absolute value of x minus a is less than delta. This becomes the absolute value of x minus 3 is less than epsilon over 7, which means the absolute value of x minus 3 times 7 is less than epsilon. But if this is true, then the absolute value of x plus 3 times the absolute value of x minus 3 must be less than epsilon. Since we know the absolute value of x plus 3 is less than 7, again, this is assuming that x is a number between 2 and 4. And then multiplying these together, we get the absolute value of x squared minus 9 is less than epsilon. And this is precisely the absolute value of f of x minus L is less than epsilon. Finally, let's take a look at the precise definition of an infinite limit. So we know that if the limit of f of x as x approaches a equals infinity, then we know that that means that the values of f of x are increasing. They are getting larger and larger as x gets closer to a. But how do we say that precisely? So look at the graph here. We have a function, and it does appear that as x gets closer to a, the values of that function are getting higher and higher. If it's truly going to infinity, then what that means is that if you choose some horizontal line, y equals m, the function will eventually be higher than that line as long as x is close enough to a, right? And no matter how high you pick that line, so even if you pick that line to be a little bit higher, eventually the function is going to be above that line. You might just have to get a little bit closer to a for that to happen. So that is what this precise definition says. It says the limit of f of x is infinity means for any large positive number m, there is a number delta such that if the distance between x and a is less than delta, in other words, if x is very close to a, then f of x is going to be larger than that large number that you started with. Let's do an example. So here we want to prove the limit as x approaches 0 of 1 divided by x squared is infinity. We already understand this limit from an intuitive perspective. We know that when you plug in really small numbers here and you square those small numbers, you get even smaller numbers, and 1 divided by a very small number is a very big number. But even though we understand it intuitively, that's not a mathematical proof. Okay, so let's go back to that definition. We need f of x to be greater than m for any chosen value of m. So let's let m be some large positive number. What we need is f of x to be larger than m. Well, in our case, f of x is 1 over x squared, and we need that to be greater than m. Now, there is a property of fractions as long as both of the fractions are positive. So if I have a over b is greater than c over d, and we'll assume that these are for positive numbers, then if you flip those fractions over, so if you say b over a and d over c, the inequality is going to reverse, okay? So if I flip this fraction over, I get x squared over 1, and this is m over 1, so if I flip that fraction over, I get 1 over m, and now this is less than. So what I have is x squared is less than 1 over m, and now I'm just going to take the square root of both sides. The square root of x squared is the absolute value of x, and the square root of 1 over m is 1 divided by the square root of m. And the absolute value of x is the same as the absolute value of x minus 0. Okay? And this, the absolute value of x minus 0, is the absolute value of x minus a, and that's what we need to be less than delta. So no matter how large a number we are given, all we have to do is choose delta to equal 1 divided by the square root of that number. So if we choose delta to equal 1 divided by the square root of m, then anytime the absolute value of x minus a is less than delta, in this particular problem, that would be the absolute value of x minus 0 is less than 1 over the square root of m. And that says the absolute value of x is less than 1 over the square root of m. And if I square both sides, that's going to give us x squared is less than. And then when I take the reciprocals, so when I flip these back over, I'm going to get 1 over x squared is greater than m over 1. But again, that is f of x is bigger than m. So as long as I choose my delta to equal 1 divided by the square root of m, that's how close x needs to be to 0 in order for the function value to be greater than m, no matter how large we choose that value of m to be. All right, and that concludes this lesson.